Hello, I am Wante Kim. I will introduce our paper Lightweight and Fast Real-Time Image Enhancement via Decomposition of the Spatial-Aware Lookup Tables. The 3D LUT is an efficient data structure. It comprises sparsely sampled input values and corresponding output values on a 3D lattice. The 3D LUT transform can directly convert input values into output values by interpolating pre-calculated values. By doing this, the 3D LUT transform can save computational costs and inference time. As combination of deep learning and 3D LUT, image-adaptive 3D LUT methods are introduced. The network generates image-adaptive LUTs for only one input image on every inference. These methods achieved better performance than the fixed one. However, they suffer from lack of spatial information since LUT transform only consider RGB values. Some spatial-aware image-adaptive 3D LUT methods overcome the limitation by combining spatial features. But this additional process introduces a substantial number of parameters and long inference time. So we analyze the spatial-aware image-adaptive 3D LUT and observe the two key insights. First of all, the image-adaptive 3D LUT methods generate 3D LUTs for only one image. This 3D LUTs significantly contributes to the overall model size and can often be redundant. Hence, we propose the decomposition techniques by low-dimensional LUTs and singular value decomposition. Second, the previous spatial-aware methods generate intermediate outputs such as spatial features and combined images. These are not cache-efficient. So we propose cache-efficient spatial fusion structure to deliver quick inference. This is the overview of our architecture. The backbone extract image context from resized image. Each generators generate bilateral grid, LUTs, and corresponding outputs. Finally, an input image is enhanced by slicing and LUT transform at once. We choose a bilateral grid for spatial fusion, because a bilateral grid has a similar structure to a 3D LUT, and it can be used to generate spatial features by slicing, which is a similar operation to the LUT transform. It is possible to apply the same decomposition techniques with LUT. From this page, I will introduce details of two decomposition technique and cache-efficient spatial fusion. First of all, we analyze the utilization rate and occurrence frequency of LUT and bilateral grid. As can be seen in results, utilization rates show that 3-dimension is redundant and 1-dimension is saturated. Most of the higher occurrence frequencies are distributed on specific region. So we formulate hypothesis. The combination of 2D LUTs and bilateral grids can serve as an alternative to 3D LUTs and bilateral grids. To verify hypothesis, we assess the PSNR and model size under different dimensions. When we change the 3D to 2D LUT and bilateral grid, the performance is maintained with significant model size reduction. In case of 1D, there are performance drop. So we decide to use the two-dimensional LUT and bilateral grid. After that, we try to adopt SVD to 2D LUT and bilateral grid. The LUT maintains its performance with up to 8 singular values. The bilateral grid experiences a performance drop from the beginning. So we decide to apply SVD to the LUT but not to the bilateral grid. Our method predict SVD components instead of 2D LUTs. The original structure for spatial feature fusion produces intermediate outputs. That means the original structure requires substantial read and write operation on memory. This is not cache-effective. So we introduce cache-effective structure. We conduct 2D LUT transforms and slicing at once. We conduct experiments on 5K and PPR10K datasets. The loss function is composed MSE loss, perceptual loss, and color difference loss. The quantitative comparison results show that we alleviate the intrinsic problems of the spatial-aware LUT method, the tremendous model size, and the long inference time. We effectively reduce them and achieve the competitive performance. This is qualitative comparison results, and our method shows visually pleasure results. Thank you for attention, and our code scan available at the URL.